Alright folks, we are back. So here, I was going to say why this is O of 1. Just go through the proof real quick. So since we're given element x, this is the node itself. We can use simply this node to replace the surrounding elements. For example, x part, next. So if x was over here, and this is y, this is z, what we can do to replace this node, simply we have to say x dot previous or prev dot next is equal to x dot next, and then next dot next previous is equal to x dot previous, which in this case would be y, this case would be z, so x is removed from the tree, which is the O of 1 operation. So analysis, hashing with chaining. How will this hashing with chaining perform? In particular, how long does it take for an element, search for an element? Given T, hashable T with m slots that stores n elements, we define the load factor, alpha, for T as n divided by n. What does that mean exactly? It's a great question. We have m slots, right? And in those m slots, a smaller number n, storage. So we'll say assume these two are stored. Okay. Then the load factor, alpha, is simply the number stored over the total number. In this case would be 1/2. Our analysis will be terms in alpha. So that's how we analyze hashing in terms of this sort of thingy. Okay. The worst case behavior of hashing with chaining is terrible. It is terrible. Okay? Because we are assuming that since it's a linked list structure, if there's only one thing, and that one thing is filled in, alpha is 1, then all the length, this could be O of n time. All n keys hash to the same slot, creating a list of length n. The worst case time for searching is O of n plus time to compute the hash function, no better than if we used one linked list. Make sense? Hopefully it does. Clearly we don't use hash tables for their worst case scenario though. Okay, perfect hashing described as provide good worst case scenario, and when the keys are static, however. The average case performance of hashing depends on how well the hash function h distributes the set of keys to be stored. Look, you can live life. You can lock in. Don't envy others. It's one life lesson outside of data structures that I hope you guys don't envy. We all start in different spots. Be happy. I'm over here because I choose to be. Okay, the average case performance of hashing depends on how well the hash function h distributes a set of keys to be stored among the m slots. On average, that makes sense. Section 11.3 discusses this issue, but for now, we shall assume that any given element is equally likely to hash into any of the m slots, independently of where any other element has hashed to. We call this assumption of simple uniform hashing. Let's go through that again. Issues, but for now, let's assume that any element has equally likely to hash any spots. Okay, let's denote the let of T of J so that n is equal to this. Okay. Expected value of nj is E of nj, which equals alpha, which equals n divided by n. O of 1 is a time suffice to compute a hash value hk, so that the time required to search for an element with key k depends linearly on the length n of h of k, the list T. Does that make sense? We assume that O of 1 time suffices to compute the hash value hk, so that the time required to search for an element with key k depends linearly on the length nh of k. Of the list, whatever this is. It's pretty hard to understand. Hopefully you guys get that. Setting aside the O of 1 time required to compute the hash function. Okay, this is how much time it takes to access the slot function. Okay, let's consider the expected number of elements examined by the search algorithm. The number of elements in the list of this checks to see whether they have a key value equal to k. We shall consider two cases. In the first, the search is unsuccessful. Second, the search is successful. So, in a hash table which collides and resolves, unsuccessful search takes an average time of alpha. Because if we assume that we're checking the certain cell, we can assume that all the linked lists are of the same size as if they were in another cell. Because again, it's the average, so we can't know for sure if they are the same or different size. Proof the assumption of simple uniform hashing. Any KK not already stored in the table is likely to hash to any of the M slots. Yo, there's a new song that I listened to. It's by Juice WRLD. I don't know if anyone messes with that. Skip for 5 seconds, sorry. Listen. Or it goes like, told her I don't need it, coding milliliters. I thought that was like pretty good little rhyming scheme, honestly. No, I kind of stole that, but it's okay. The expected time to search unsuccessfully expected to be this, which expected length of this, thus the number of elements is equal to alpha, right? And then plus 1 since it takes that much to do the computation of h of k, and then also the search. The successful search is slightly different since each is not equally likely to be searched. Interesting. This is very interesting. Instead, the probability the list of search is proportional to the number of elements it contains. Nonetheless, okay, this makes sense. Well, it's the same, right? But I don't get this probability part. Maybe I'll show you the theorem a little later. Or I guess we'll go through it right here. Follows by a successful search of this time. We assume the element being searched is equally likely to be any of the n elements, right? Because it has equally likely the number of elements examined during a successful search for element x is 1 more the number of elements that appear before x in x's list. Because new elements are placed in the front of the list, elements before x in the list were all inserted after x was inserted. find the expected number of exam, we take the average over the n elements in the table plus the one expected number of elements added to the list. Okay? So I don't really get this, but it seems to be a pretty cool proof. You guys can look into it. I might come back to this proof later. I'm going to put it in my notes to do. But since I am trying to speed through a lot of this information, I'm going to just write it down in my to-dos. So I'll switch to here. Page 261. Proof equals read. Just so we keep on moving and I don't waste a lot of more of your time, because I know your time is pretty precious. Thus, the total time required for a successful search, including the time of computing hash function, is this. It's literally just both of them added, but the alpha then just reduces to this. Analysis mean. Analysis means the number of hash slots is least proportional, yada yada yada. And when it's doubly linked, support all involve one on average. Go hash functions. So what makes a good hash function? It's approximately the assumption of simple uniform hashing. Each key is likely to hash any M slot independently of where other keys are hashed to. Unfortunately, we have no way to check this condition since we rarely know the probability of distribution from which the keys are drawn. Specifically, what this says is a hash function that is good is we can't predict that by a certain input we're going to get this output. It is kind of confusion. But the function will always return the same input or output no matter. Always return the same output with the same input, if that makes sense. So if I just plug in 1, I might get 3. But every time I'm plugging 1, I'm going to get 3, no matter what it is. Moreover, it might not be drawn independently. Occasionally, we do know the distribution. For example, we know that the keys are random, real k, independently and uniformly distributed. The hash function is something like this. This is simple uniform hashing. In practice, we employ heuristic techniques to create a hash function that performs pretty well. Qualitative information about the distribution of keys may be useful in this design process. For example, consider a compiler symbol table, which the keys are character strings representing identifiers in program. Closely related symbols such as points and points are very often occurred in the same program and can get a little confusing. Good hash function would minimize the chance of this getting the same slot, especially when you're looking through that dictionary. Approach to this would be the division method, which is then laterally discussed, which allows us, we choose a prime number unrelated to any of the patterns of the distribution keys. Finally, note some applications require stronger properties, especially in security, compared to just adding it into a public database that everyone can access and they're not trying to hide anything. For example, we use close far apart. This property is in linear probing. Interpreting keys as natural numbers. Most hash functions assume that the universe of keys is in the set of this. If the keys are not natural numbers, then we find a way to interpret them as natural numbers. For example, we can interpret a character string as an integer expressed in suitable radix notation. Thus, we might interpret the identifier point as a pair of decimals. ASCII set. This becomes usually this. In context of a given application, we can usually devise some method for interpreting each key as a possibly large natural number. In what follows, we assume keys are natural numbers. So let's continue back. The division method. Division method for creating hash functions. We map a key k on to one of m slots by taking the remainder of k divided by m. That is the hash function. H of k is equal to k divided by m. Okay? For example, the hash is table as this size, k, and the key is 100. Then since the only divisible is this, which is quite fast, usually want to avoid certain values for m, especially when in magnitudes of 2, simply because 2 is the lowest, and it will either only be 1 or 2. That is going to be the remainder, right? This is a prime not too close to the exact power of 2 is a good choice. Maybe 2001, I don't know if that is. But it also has to be like small enough, right? The character is 8 bytes, we don't an average of 3 elements for unsuccessful search. So we allocate a hash table with a size of 701. Choose m equals because the prime is near 2000 divided by 3 does not. But not any near power of 2, treating each key k as an integer or hash function would be this. The multiplication method is pretty similar. It's taking, for creating hash functions, operates in 2 different ways. First, we have to multiply the key k by constant a, and in the range between a being of 0 and 1, we extract the fractional part of k of a, and then we multiply this value by m, and take the floor of that value. This is what we have. Exactly when you mod by 1, that's essentially doing the floor, and multiplying that together with m. Only thing is, I'd probably put the m in here and take the mod of the whole thing, or maybe just do this, simply because they say we multiply by m and then take the floor. But here they're doing it before. I don't think it should have much of a difference, but assuming m is strong, then yes, it could carry over a little bit that it won't be able to carry over. See, why advantage of multiplication is the value of m is not critical. We typically choose the power of m to be this. And most computers follows a. We restrict a to be a fraction of the forms of this, and the result is a 2W-bit number. For example, a is to be this, likely to work reasonably well. And then it shows us how this is related to this, related to this. So universal hashing. This is starred, so I'm gonna go through this probably in the most depth. So if a maliciously adversary chooses the keys to be hashed in some sort of fixed hash function, then the adversary can choose n keys that all hash the same slot, yielding to an average retrieval time of O of n. Does that make sense? Any fixed hash function is vulnerable to such terrible worst case behavior. The only effective way to improve the situation is to choose the hash function randomly in a way that is independent of keys that actually are going to be stored. This approach is called universal hashing. Does that make sense? Basically, so they're saying fixed hash functions that use a key are very easy to actually back solve. So it could just be easier to do this universal hashing where you can randomly choose independent of what keys are being chosen. Okay, this approach is called universal hashing and can yield probably good performance on average no matter which keys the adversary chooses. In universal hashing, at the beginning of execution,